Okay, good evening and welcome. My name is Tony Beasley. I am the director of the National Radio Astronomy Observatory. What we're going to do tonight is have a listening session about a project of NRAO called the Next Generation Very Large Array. So with me here tonight is Dr. Trish Henning. She is actually the director of the Very Large Array down in Socorro. And between the two of us, we're going to give you an introduction to NRAO and an introduction to the Next Generation Very Large Array, and give you all an opportunity to ask questions and really explore and try and understand what we're hoping to do in future. So I'm going to start by giving you an introduction to the National Radio Astronomy Observatory. We operate radio telescopes for the US and international research community. So some of the telescopes we operate, there's the Very Large Array telescope that we're very proud of here in New Mexico. It's 27 antennas on a track to the west of Socorro. There's the Very Long Baseline Array. This is 10 antennas distributed across the United States, continental United States, and in Hawaii and St. Croix in the Virgin Islands. Now, while that telescope is situated across the Northern Hemisphere, the Western Hemisphere, it's actually operated out of Socorro. It is also operated out of New Mexico here. We have the Atacama Large Millimeter and Submillimeter Array. This is a telescope that operates at a higher frequency, and at those higher radio frequencies, you need to be above the water vapor and a lot of the oxygen in Earth's atmosphere. So we put millimeter telescopes like ALMA on the tops of mountains and on high locations. And so this is at 16,500 feet in the Atacama Desert of northern Chile, and it is high. And then finally, this is the Robert C. Byrd Green Bank Telescope. This is a very large single dish telescope. It's a little different in the way it operates. A large telescope that we operate in Green Bank, West Virginia, about 4 hours drive from Washington. Now, each of these telescopes is the best of its type on Earth. It does incredible radio astronomy. Each of them does incredible radio astronomy, and we're incredibly proud of what they do. And this is kind of what they do. This is the night sky over Green Bank. This is what you would see if your eyes could see radio signals. And, you know, at first glance, it kind of looks like the night sky, but it's not. When you look up in the night sky and you see that, you're looking at stars. And actually, you're mainly looking at stars that are relatively close to the Earth. When we look with our radio telescopes and make an observation like this, each of those dots is a galaxy. It is actually a very distant standalone galaxy, just like the Milky Way. And in fact, you can see some of these larger kind of woofly structures. That's actually radio emission from our galaxy that's in the foreground here. So each of those little dots, if we were to use some of our radio telescopes, would blow up into objects like these. If we had enough resolution, we would actually see this. And what you're actually looking at here are what we call active galaxies that you notice that each one of these panels, top left, top right, and the three along the bottom there, there's kind of a white dot at the center. And that is the black hole. That is the place where there is a supermassive black hole, millions and sometimes billions of solar masses, that is sucking material down, eating gas and dust and so on. And through some process that we have some understanding of, not perfect, they produce these amazing clouds of radio emission. So you kind of get two jets of radio emission that go out in different directions, and then eventually those jets kind of hit the edge of the cluster material, and you actually get these large radio loads. And so, as I said, each of those dots that you see in that night sky view that your eyes would detect, if you get enough resolution, they're going to look something like one of these. So nearly everything that we see in there is difficult to explain. As I said, we have some models of how it all comes together. But in reality, this is part of the reason, amongst many reasons, that we do radio astronomy. We are trying to understand the universe at radio wavelengths, what we see. This is another example. If you look at the diagram on the left, that's actually a low resolution image of the center of our galaxy. If you follow it up to the right with slightly higher resolution, you can keep zooming in, as those red boxes do. And eventually on the bottom right corner there, you see just under the 3.6 centimeter thing, that's our white dot. That is the black hole at the center of our galaxy. It's called Sagittarius A star, and it was discovered about 50 years ago. And so in the same way we look at other galaxies and we kind of look at those processes, we can look inside our galaxy and we can see a lot more because it's a lot closer. Another example is if we can actually look at, in distant galaxies, we can detect supernovae. This is a process where a massive star collapses and then eventually expands out and produces something we can see. The video is not working here, but that's okay. So using those supernovae, we can actually detect the distance to those objects. And that's a way we can set up a distance scale in the universe. So these are all the kind of the different science cases that we have. This is a galaxy. On the left, you see kind of a picture of the radio emission from the galaxy. And that kind of gives you some indication of where stars are being formed, mainly. This is a galaxy that's a little younger than ours. And so it's going through a burst of star formation. Our galaxy, less so. And on the right, using our radio telescopes, we can actually trace the direction of the magnetic field in this galaxy. And what you see is that the spiral arms and the magnetic fields tend to align. And that is, in fact, part of the way that stars are formed, using the collapse of gas and with magnetic fields contributing. And so, again, this is another great example of the sort of work that we do. And then finally, this one, deep down in the center of this, you can kind of see the white area. That's the optical galaxy. That's what you would see with your eyes. If you actually make a radio observation of that galaxy, you see all the blue material. That's hydrogen gas. And in fact, most of the universe is hydrogen gas. A lot of the universe is. And so what you detect from this is that the hydrogen in the galaxies is much more extends over a much larger region than the stars do in the galaxy. So if you really want to understand how much mass there is in the universe and how these galaxies form and how all these clusters of galaxies operate together, you need to be looking at all this material. And that's the contribution that radio astronomy makes to the science. So there are kind of four classic reasons why people do astronomy. There are more, but the four that I like. One is to find our place in the universe. So down through history, there's always been a tradition of doing astronomy. People look out in the night sky and they kind of figure out, where do I fit into all of this? Culturally, mankind has been doing this for thousands of years. People have been looking in the sky, seeing shapes in the constellations, seeing Orion, the Hunter, and so on. It is part of us. It is part of our sense of exploration. The cosmic laboratory, when we look out into the universe, when we look on the surface of the sun, and we look into these black holes, we're looking at places in the universe that are very, very different to anything we can make here on Earth. They can be hotter, they can have a higher gravity, they can have a higher magnetic field, and so on. And so if we really want to understand physics, the cosmic laboratory is a way of taking your understanding of how atoms and molecules work and then putting them in a situation that you could not produce here on Earth and making a prediction about how they will behave or how they will look. And so by looking out into the universe in these hot magnetic field, high gravity locations, we're learning about the physics of the materials that surround us here on Earth. And so, it's a valuable tool. Technology development, like these antennas that you see, to do these sorts of observations, you require very sensitive radio equipment. So all of you are probably sitting in here with a cell phone. And your cell phone, if I was to transport you all to Pluto right now, your cell phone would be still a very bright radio signal to our radio telescope. And so to make sure that we're only really looking at the astronomical signal and to do the best job we can of detecting those signals, we develop new technologies. And so in that cell phone that we're talking about, besides your lifeless body on Pluto, is actually an amplifier, which kind of came out of radio astronomy, and there's a camera, which came out of optical astronomy. And so the technologies we develop as part of our scientific endeavor eventually flow on and contribute to society, and they have huge impacts to people. And then finally, growing STEAM interest, science, technology, engineering, arts, and mathematics. So people like astronomy. It's a very interesting topic. It is a great way to get kids interested in maths and science. And so if you really want to kind of create a scientifically literate society and you want to have generate an interest of people that might go into these incredibly important STEM careers, STEAM careers that we're interested in, astronomy is a lovely way to do that. And so to support that, we have a lot of education and outreach programs at the observatory. We have students from K to Grey, as we say. We have trainings and we have courses, and we bring people in and we have kind of simplified versions of the telescopes that people can operate and so on. And this is how you kind of get people interested and excited and engaged in the research that we do. And this is one of the truly fun parts of what we do. Now, looking ahead, well, the VLA has been in New Mexico, down near Socorro there, for upwards of 50 years at this point. And it is still the world's best radio telescope, without a doubt. But like my knees, it's feeling its age. And, you know, it's important to think about what is possible now. And technology has certainly changed. We are capable of building a very different, far more powerful telescope today. So the project that we've brought to life is what we call the Next Generation Very Large Array. And the goal of that project is to combine the existing VLA at the site and combine the very long baseline array distributed across the United States into one array, and then increase the number of antennas in that array by an order of magnitude, by a factor of 10, to dramatically increase the sensitivity. So back in 1970, that was unthinkable. And today it's totally thinkable in terms of what we can do regarding technology and data and being able to do the science that you could get out of that instrument. And so this is the project, the Next Generation Very Large Array. If you look at this diagram here, if you kind of start on the top left, that's about the scale of the current VLA, that sort of 5-arm spiral starfish thing there. That's sort of about the VLA now, about the same size. Now, if you kind of go to the right of that, you can see that we want to continue those spiral arms out through the desert Southwest. So we're going to go into Arizona and into Texas and down south actually into northern Mexico. And then on the larger scales, which you see on the right here, we actually link up with those VLBA antennas on the longest baselines. And so the VLA currently is 27 antennas. The VLBA is 10 antennas, so together that's 37 antennas. We are talking about 263 antennas with the Next Generation Very Large Array. And as I said, the technology and computing and our ability to make these antennas, we are now capable of building this much more powerful array. Just a little bit of information about the design of the array. It operates between 1.2 and 116 gigahertz. So 1.2 gigahertz is about the frequency of your cell phone. And that's why if you ever come to the VLA site, we ask you to tell your cell phone off. 116 gigahertz is, actually, frankly, far above anything that you commonly have experience with. But this is a new area of the spectrum for the VLA. And so there's a lot of exciting science to be had there. And we've kind of mapped out the way that we want to build the array with 18-meter diameter antennas and some 6-meter diameter antennas. Here's an example of the antenna. You can actually see, get a sense of the scale from the truck at the bottom of it. So to actually, if you're going to go ahead and build 263 of these things, you need to build one of them. And we have done that. Back in April, we actually handed over from the manufacturer one of these antennas at the Very Large Array site. And this was a fantastic contribution by the National Science Foundation to the project, helping us prototype this antenna. And over the course of the next 6 to 12 months, we'll be making sure the antenna is the right antenna and get the job done. And then slowly what we want to do is continue to move on and begin the project. That's a kind of an old picture of it being constructed at the VLA site. That is the antenna that in April was handed over to us. And so it's a pretty thing. And we have a Very Large Array open house on Saturday, and you're all welcome. If you can find it online or just turn up, you'll get a good look at that antenna. Should be a lovely day. To give you a sense of beyond astronomy, some of the other things that we do, this is just a very cool thing that we've been doing with the VLA. We've been transmitting from the Greenbank site and receiving it with the VLBA sites and the VLA. And what you can actually do is look at some of the craters on the moon. And so this is a blow up at about 9 meters per pixel of an area on the moon. And it sort of looks like there's walking trails between things. They're not, they're lava tubes, actually. So when the near Earth object hits the moon, it forms a lot of molten material, and that flows in channels, and that's what these channels that you see in the diagram are. And so one of the things we do want to do is do more geology on the moon. I guess it's not called, maybe it's still called geology. I don't know. Okay, so that's just kind of the picture. You know, we are very excited about the ngVLA. What we're hoping to do is to get all of that amazing science out of the new array. And over the course of the next couple of years, we are reaching out to the community. We want you all to know what we're doing with the VLA, be excited about what's coming next, and to participate as you see fit. So thank you. I'm going to hand it over to Trish now, and Trish is going to give some more details about the benefits to New Mexico.
Great. Thanks, Tony. Hello, everybody. As Tony mentioned, I'm the director of the VLA, and I'd like to stress that we are still very proud of the VLA. Hundreds of scientists every year want to use our telescope. It's still fantastic, but as he said, it's been around for quite a while now. We have done some upgrades as we can, but technology has, thank you, Karina, has moved on. And so we can sort of leap into the future with a much more capable facility that's going to replace both the VLA and the VLBA. Now, I'd like to focus on New Mexico for my couple of slides here. And as I think you all know, actually, let me ask, how many people have been to the VLA? Okay, almost everybody. And so I hope that the rest, first of all, if you've been, you're welcome to come back and visit. And if you haven't been, I really do hope you get a chance to go see it in person, to really get a sense of scale of the kind of grandeur of the thing. So we're still very proud of it, but it's time to look to the future. And so this icon in New Mexico, I think the ngVLA will be the next icon in New Mexico. The core will be there and most of the antennas will be in the state. So what's going to happen in New Mexico? Well, the construction of the ngVLA is a multi-billion-dollar endeavor. It's a big project. And we're anticipating that over $1 billion of that would be in New Mexico during construction. And so obviously that's a big thing, just the construction phase. Looking into the sort of permanent future and what that looks like for the ngVLA. Right now we have about 220 employees in the state of New Mexico at NRAO, and that's going to go over 400. And so this is a large jump. And it's not just astronomers. In fact, it's not many astronomers we need. We need all kinds of people to be involved with ngVLA. We need electricians, we need welders, we need engineers of all kinds, electrical, mechanical, civil. We need data science folks, data transport folks. And so it's a big endeavor. And so that's going to be a big step for us. So right now, New Mexico is world-renowned as the host of the VLA. People from all over the world want to use it. And that's just going to grow with this extraordinarily capable, more capable facility that we hope to build. Now, along with the scientific and technical part of this, we want to become a destination for STEM education as well. So in parallel with ngVLA plans, we are looking to build an exciting learning center, which will impact, we hope, all school kids in the state of New Mexico, to replace our visitor center and have a sort of excellent, awe-inspiring, hands-on educational experience for kids, for visitors of all ages. And along with that, we're planning on building on our current educational efforts and do teacher development. So we would love to see every kid in New Mexico experience this amazing place. And we want to help prepare through their teachers' development, right, so that they can learn about it before they come. So big plans. Now, right now, you've heard Socorro mentioned. That's where our VLA headquarters is. The telescope itself is about 50 miles west of Socorro. And so we have a presence out in the desert, the headquarters in Socorro. But ngVLA is a very big thing and will be more of a distributed New Mexico facility. So yes, there will still be activities out near the dishes in Socorro, perhaps in the town of Magdalena, halfway between Socorro and the telescope core. But it has to grow and it has to spread. We anticipate important activities in Albuquerque. Now, we already have a project office for the ngVLA in Albuquerque. It's modest at this time, but the growth will happen there. Okay, so when is it all going to happen? Well, so kind of depends on the money, the details of this, but you can see we've already passed some very important milestones in the last few years. Our colleagues have endorsed this concept in the decadal survey that happened in 2020, saying astronomers really need this. We've done other reviews. And so where we are now, we're very focused on that prototype antenna. So while we are still conducting observations with the VLA, we have this prototype antenna, which has risen up in the desert. And as Tony has mentioned, we need to test it very, very carefully because you want to learn everything you can about the first antenna before you build, 262 more. You want to get it right. And then another thing about the excitement out at the VLA site is the supercomputer, which takes all the data back from all the VLA antennas, has capacity. We can plug in this prototype antenna and actually plug it into the array. And so do testing of that antenna with the array, which is very powerful. And so we continue with design. Now, getting to the full construction, there are hurdles that need to be passed. They should be passed. We need to get it right. We need to get the design right. And then the larger dollars need to flow for that. So we are looking to have this become more and more palpable, more and more tangible through the end of this decade with early science. End of the turn of the decade, around the turn of the decade, and then full operations into the 2030s. Meanwhile, our plan is to build this learning center. So the learning center will be there in the shadow of the VLA, which is already awe-inspiring. But then when the ngVLA rises up, then it'll be there. And we are at the stage there where we are we've hired an architect. And that work is occurring to get to design. And we're continuing with frankly, the fundraising stage to get to a full build. But I think we have talked plenty. And really the point of tonight is to hear your thoughts, your questions, your comments. And so please feel free, speak up, give us your thoughts about the picture and what questions you might have.
In New Mexico, especially, in Santa Fe, anytime somebody wants to build wind farms and solar farms, the neighborhoods go absolutely insane. So how do you go about placing 263 of these things in places where every single neighborhood or rancher and all this are going to be up in arms?
So the question was some comments about placing things in New Mexico. The difficulty with locals and people adjacent to what you want to construct. Yeah, it's a problem. The VLA site itself currently we have a good relationship, I think, with our ranching neighbors and so on, and so it is a lot more antennas, and so that is a discussion we will be having with them when we look at the diagram of more antennas around the state. I mean, a fundamental issue is the Pluto issue I mentioned earlier, which is we don't actually want to be near people at all. And so, our idea of a great site is, at the very back paddock of someone's farm, 3 miles away from anything with a good fiber connection and electricity. So, yeah, I think one of the things that we do as part of siting the array is that we factor that. that we don't want to be putting this on top of a schoolyard or something like that, that we want them to be away from towns and people. And there is an environmental review process that we'll go through, and people will inevitably have comments. We have the ability to place these antennas independently. So, I showed you the diagram and the lovely spiral and all that, but actually it's perfectly random in an interesting way. We don't want to put the antennas in some regular chessboard pattern. And so we have a lot of flexibility, even on the scales of around New Mexico, to move the antenna 20 kilometers that way. Right, so that's kind of the answer. So that the place where that answer is not perfect is actually exactly at the center of the array with our ranching friends, and that's why we've had this meeting with them, and they're certainly aware of the project. Yeah. Okay. Please.
Related to that, actually, the problem of putting the dishes into developed areas where you might have to find a way to shield it from local radio emissions.
You want to view that?
Yeah, that's a great question. So
Repeat the question.
Oh, I'm sorry. So talking about placement of antennas again, and a concern about if we're putting it into developed areas, do we shield it from person-made emissions?
Yeah.
And so the first thing you do is try to avoid person-made emissions. And the VLA, if you've been out there, is kind of remote. It's on a flat plain, which is ringed by mountains. And that's our shielding strategy, is to put it in a place where there is shielding. Now, when you have many antennas in different sites, you're not necessarily going to get that terrain shielding, although that might be part of the GIS.
It's
Okay,
hard, yeah.
that's a difficult thing. So again, people radiate. The amount of radio emission that there is in any given location kind of scales with the number density of people. And so you try to avoid the people. So we won't be putting these in the middle of towns and so on. Yeah, I don't know if there are
No, I
other
think it's the right
particular
answer. Like,
strategies.
20 kilometers out away from towns and Hans is good. I mean, the current VLA has State Highway 60 running through the middle of it. So, we are somewhat immune to some of this, right? It's not catastrophic, but you're absolutely right. Like, putting one in the middle of downtown Santa Fe was a bad decision. I mean, we wouldn't do that. But, as long as you're within, if there's not a lot of people within 5 to 10 kilometers of the array, we have antennas around the US, and we can operate that way.
Mhm.
Yeah.
Two quick questions on a similar thing. And I may have mentioned it. Is the backhaul all fiber, or do you have others? Are you gonna have to place right of ways and easements and whatnot to get fiber dedicated? What is the actual backhaul plans? And number two, to the RFI kind of question, ground is one thing, but New Mexico airspace is. You've got an MOA sitting right on top of the BLA now, and there's a lot of military traffic, a lot of emerging electronic traffic. So what is the limitations or concern for airborne?
So 2 questions. One was about backhaul of data, and are we relying on fiber or other means? And the second question is, what is the interaction between the way we're observing and military operations that are going on? So question one, it is largely fiber. We digitize the signals and send them back. On the plains of San Augustine, and possibly within 100 kilometers or so of the VLA, so that general region, we would, potentially we'd be digging trenches and bringing the fibers back ourselves. Once you go to any sort of reasonable distance, you're in commercial fiber. You have to trunk your site back to a commercial fiber and then bring that back through somebody's commercial fiber. And so that is, in this process that we've discussed a little bit, that's one of these kind of interesting constraints. I can find a cheap, quiet, amazing place, but if I have to haul fiber 50 kilometers, it's not financially viable. So if it's not obvious in our diagram, but as you get away from the VLA, every one of those antennas is right on top of a trunk fiber. So that's the way that goes. The other point you mentioned, and this is kind of looping back to this interference issue, we deal with all this stuff all the time now. And it is an interesting point that about 30% or more of the interference we get into our antennas is coming from the sky. It's not so much aviation, I will say, although there's a little bit of that. A lot of it is now the commercial downlink satellite. It's SpaceX and all of that. We work with our SpaceX colleagues, and so we've made some progress on that. This thing you've probably seen advertising where your cell phone can talk directly to a satellite, that's super bad for us. That is not good for us. So we are kind of aware of that. But the particular thing you mentioned about the military and sort of interactions with White Sands and other things that are going, we actually coordinate pretty well. They tend to have fairly focused areas of the spectrum that they're operating, and we inform each other of what we're doing. So we don't tread on each other. It's not too bad. Yeah, please.
So I have to confess, I'm a New Mexico Tech alumnus. And I was wondering, it looks like to a degree you're de-emphasizing Socorro as the nexus of operations and data analysis. Is that true?
So the question was, what is Socorro's long-term future in ngVLA? Is there a de-emphasis? And do you want to?
What I would say is that we're growing other places. So there will be a very important presence in Socorro going forward. That absolutely. I mean, that's, what we're trying to do in some ways, so where the antennas are, have you been out to the VLA? Yeah, okay. So we have our tech services area, and we have folks, about 60 people who work out there. We do our repairs and we do fabrication. We do a lot of work on the cryogenics and the fiber and all that kind of stuff. And in some sense, we're creating our own interference. So one thing we are thinking about doing is shifting some of that activity, just maybe Magdalena, right? Just to get it. You don't have to be right there. But Socorro, I mean, we've noted, and again, this is provisional. This is part of the overall design, which is still under development. But you see, Socorro mentioned a couple of places there, and right now, Array Operations Center. Well, it is, right, and so, but we think that when you have centers like science or a data center, that doesn't have to be in Socorro, and there are advantages to having it in a larger city where more people will be. So what I see is growth will be happening where we don't have much footprint now, right? But that doesn't mean the rest is
No, I think that's
zeroing out.
That's a fantastic way of describing it. I think I would also say that it is possible that we could do more growth in Socorro. Actually, growing in Socorro is really hard right now in terms of accommodation and all of that. So that is one of the parts of the solution space here is that, okay, Trish described needing 150 people. There's nowhere for 150 people to live in Socorro right now. And so that's why, as Trish very elegantly said, what we're trying to do is grow elsewhere, but there'll still always be this major, certainly in the engineering role, there'll be a major footprint in Socorro.
I'm sure you're aware that Tech is emphasizing STEM for incoming students. And that's a growing area of concern in that institution. And I hope, there's some synergy there.
The comment was that Tech is emphasizing STEM for incoming students, and absolutely, we do a lot of our hiring with from Tech graduates, right? So we have a pipeline of folks who, for many, many years, have become really critical members of the staff. And we have student involvement and such. So yeah, no, tech is very important to us, and that's absolutely. But we're going to be big, and so there'll be other areas.
Anything with very low frequencies, really low, long wavelength frequencies, like almost not audio.
Question was, what have we done with low frequencies? So at the current VLA site, there is a low frequency telescope. It's actually run by UNM. Up in Albuquerque, but I don't think it's kind of low at the frequency you're saying. I mean, I think that telescope goes down to maybe 20 megahertz or something like that. Below that, the size of the instruments are getting massive, or you're a half dipole or something like that. So those lower frequencies, there are places around the world that are still pursuing that sort of radio astronomy. that is where you really get hammered by RFI, you know.
Or they have antenna arrays that are like many miles wide.
Well, there's a huge project underway internationally at the moment to build what's called the Square Kilometre Array. And one of their projects is a low frequency telescope that I don't think goes, maybe it goes down to 20, it goes down to 50, I think. And so they have Christmas trees like this kind of big. And I think the eventual plan is to have like 135,000 of them or something or other. So absolutely, people are pursuing that. And, in fact, those interesting radio galaxies with the jets and so on that I showed you, they look beautiful at low frequencies. They're very exciting. And so that's a very exciting part of what we do. Yes.
Third question, a few others. The third question is, what's the difference between an offset parabolic and an offset Gregorian?
So the question was what is the difference between are you asking what's the difference between those two phrases, or between why do we do the two different antennas? So fun fact, if you build a symmetric dish and it's going to have some kind of receiving element in it, this whole thing has got to be up enough so that it can move. And so in an interesting way, symmetric, they call it Cassegrain dishes, have to have a very large pedestal, and this is just a whole lot of steel. Yeah.
A parabolic and a Gregorian reflector.
Gregorian refers to what the shape of the subreflector is. And I'm sure I'll get this wrong. If the subreflector is concave, it's Gregorian, and if it's convex, it's Cassegrain. I think that's the answer. Yeah. And you had another question? Yeah.
Another question is, the learning center is going to go out of the site, and you still will be bringing students in the way you do now, which is great. Do you have any further offsite outreach as well?
The question is, so this learning center will be out at the VLA and then ngVLA site. Do we have plans for more distributed facility? And I think the answer is no. We have plans for distributed activity, but the thing is, the telescope is amazing to be near, and it's just exciting to be there. And I have watched kids come on tours and to the open house, or just with family or whatever, and just seeing the place makes a spark, and we want to build on that, right? But we at this point we do go into schools. We have outreach activities. We have
traveling planetarium,
and the traveling planetarium goes out around the state. So we will continue to do that. But we want to leverage the awesomeness of the site.
A separate line for the funding of the learning center, or is it part of the ngVLA?
The question is the funding for the learning center separate from the VLA, from the ngVLA funding? Yes, it is separate from the ngVLA funding, indeed. Well, at this point, we've been working, also NSF, what's the question? So right now, we're very grateful for some capital outlay support from the state of New Mexico. We received $1.8 million last year. We received $1 million in federal funds through Senator Lujan's office, HUD money, and so not NSF funding. Now, the NSF does support our education and public outreach efforts, but the fundraising for the Learning Center, we continue to partner with the state, and frankly, private donors is where we need to be looking. So we're doing all of the above.
Yeah, I think through the Learning Center, NSF will contribute, as Trish said, in terms of some of the exhibits and programming in there and so on. But as kind of an interesting part of the way that the Learning Center is coming forward is we're actually trying to give the state and individuals some buy-in to this process and some ownership over, what could be a very important educational initiative for the state. And so I want to walk that trail 11 times and fail before I actually turn back to the NSF and say, well, we probably need the money for this too, which is going to seem rude on top of the rest of it. So yeah, that's why, as Trish mentioned, we have a capital campaign out there, and the state has been fantastic, and we're going to continue to walk that for a while. Other questions? Yeah.
It seems like there's been a big move, especially since the advent of gravitational wave detection toward like multimodal, astronomy, and you got GWST, you got this. Is the ngVLA explicitly in any way related to that? I guess particularly vis-a-vis gravitational wave, like where you can then get electromagnetic data and the gravitational wave data from an event. Is that kind of part of the?
Yeah, absolutely. So there are 4 or 5 major science cases for ngVLA. One is looking at planets forming around nearby stars. Another one is looking at the formation of galaxies throughout the history of the universe. There is exactly one to look at this, what we kind of call the transient universe, is that there are, we have this whole suite of other fantastic US and international instruments that are making these amazing detections of gravitational waves from black hole binaries collapsing and stars exploding and so on. And absolutely, a big part of the science that ngVLA will do is to follow up on those objects. And that it's not easy to spot from the diagram, but that's actually part of the reason why you have a lot of antennas. So when we have, even it's true with the VLA as well, when we have all of these antennas, there are times when they're all looking at the same thing. Right? But there are a lot of times when they're subarrayed. So these guys are looking over there and these guys are looking over there, and we can pick out multiple objects in the sky and observe them in parallel simultaneously. So it's a little hard to do when you got 27 antennas. If you need more than 9 antennas to make sense of it, you get 3 of those. Well, if you've got 263 antennas, you've got many more of those. And so that's how, for example, with Reuben coming online. And, if I got a list today of 10 amazing things in the sky I should look at absolutely right now, with the VLA, we get through a couple of them, I guess. But with ngVLA, we would plow through all of them because we could subarray out to get them all done. So, yep, the transient universe lies ahead, and that is a part of our science case.
I've read where they originally thought that gravity waves were kind of a rare thing, and they're finding out they're all over the place.
They're hard to detect, though.
Yeah.
What is it? The LIGO's detection of the gravity wave involved a deflection, which is the same thing as having the Earth and the Sun move apart by the width of a piece of paper.
Yeah.
So that's the detection limit. So they're doing a lot of it, but it's not easy. Any other questions? Yes.
This is maybe more historic, but it just dawned on me when you mentioned 1970. And when the VLA started and you're doing your science, these things didn't exist.
Mm-hmm.
So you obviously developed techniques or rejection techniques, or I think that would be an interesting thing to understand your defense mechanisms as they've evolved from not having to worry about these things. As you mentioned, the highway's going right through, and everybody's got multiple of these things in their cars. And the car, and all the computers in the car, and everything they're emitting. These bright lights have to be just all over.
Well, remember I said, so your cell phone transmitted about 1 watt or something like that. So 1 watt on Pluto is 1 Jansky. It's a fun fact. And so that's a bright radio source in the diagram I showed you, one of those dots in the sky. So, we can detect that with the telescope pretty easily. But it is only 1 watt. And you're right, there are many of them. Everyone has one in here. But your microwave oven is 700 watts, right? And your washing machine is probably 200 watts and so on. So the phones are a problem, and absolutely we deal with them and we ask people to look after them at the site and all of that. But it's not just that, it's everything. It's your car. Modern cars are actually better. But in Greenbank, for example, I didn't kind of get into it. When we have the arrays of antennas, they are interestingly a little more immune to interference, because what we're actually doing is we're taking the signals from 2 different antennas and multiplying them together. And so the interference has to get into both of these guys, down the throat. And that's not easy to do in an interesting way. Your phone, if you're standing beside the antenna here, your phone might hurt this one, but this one could be 10 kilometers away. Well, green bank is one dish. It's one pixel. It's like having a camera with one pixel on it. It's an amazing pixel, but it eats everything. It sees all of this stuff coming in there. So we have a quiet zone around green bank that we actually control that basically runs for essentially 100 miles in every direction around the telescope. And so, it is the case that we are far more sensitive in certain situations, but even there, we've developed techniques and technologies to deal with some of this interference stuff. So it is a problem. I would say, the satellite internet thing and the direct-to-cell thing is it's an evolving problem in some sense, but it's a big spectrum, and we're pretty clever, and we're going to get past it. So, it is something we keep an eye on, and we'll coexist. Other questions?
I can do another funding question.
Sure.
Is there funding for that preliminary design review in 2026, or is that something that has to go through the appropriation stuff?
No, so at the moment we're okay. We are continuing, the National Science Foundation is doing an amazing job of continuing to fund our design activities and so on. So, exactly when we'll get to preliminary design review, not helped by current situation and all of that. But we are steadily moving towards that. So I like Trish's dates, and we're trying to march toward those. NSF has been a fantastic partner. Actually, we have other partners too. The US Naval Observatory is a fantastic partner. And so there is money flowing towards this concept and so on. It's just kind of the way that instruments come to life. You have to do the design and get the reviews done. So I actually kind of suspect that our preliminary design review will be late next year or something like that. And we are funded through those activities. Yeah.
Two quick questions. This is great. Thank you. One is physical security. If you do get these things located, there's gonna be somebody there, even camera and alarm. It's gonna be a little while to get there. So physical security, I'm sure you've thought about it. And the other, and it might be way ahead of public access or data embargoing. Like for example, a lot of the policy now is to make Rubin and James Webb very, very quickly available to the open. I can log on and download or frame images. Any thoughts?
Sure. So the two questions there was one about physical security at the antenna sites. And the second question was, a question about data access and what the data access policies might be. So physical access is an interesting question. Ultimately, these are federal facilities. And over the course of decades here, that's kind of been enough that we don't tend to have a lot of problems in that. All right. Now, the antennas are locked and all of the equipment is locked and so on. It's a bunker at some level. But the reality is that we have not naturally had a whole lot of problem with that. I may regret these words in years to come, but that's the way it has been. In terms of a camera, yes, we have that sort of facility. And you are absolutely right. All we can do is kind of record what happened. It's not like we have someone, 300 yards away who could suddenly leap out of their house or something like that. Is a concern. That, again, is one of these factors that we would put into the assignment of where we would build these things. So I wouldn't necessarily build these things next to a quiet exit on a major highway, for example, that kind of thing. Regarding the data access thing, NREO has an existing policy, which is that our data is available to anyone after 2 years, right? That is long, right? But that number has been kind of chosen deliberately, because if you look at the teams that actually, create these observations and they have to reduce the data and produce the information out of them, it takes them on average about 2 years to get that done. And so we try to line up that period with a reasonable period for them to produce the data. It is absolutely true. There are parts of our community that are going the other way and making data instantaneously available. So, there are arguments for and against that kind of thing. I think the argument that someone who has not had anything to do with the creation of a data set is going to be able to download it and do something amazing with it, it's possible, and there are situations where that is possible. our data is very complex and it requires a lot of post-processing and a lot of understanding. That's just not going to be, it's not going to be easy for anyone who's not sort of written into whatever the project that took the data was. So the proprietary period is a healthy debate. We're debating it right now. But in general, what you're going to find is I suspect that the data from ngVLA will be available to everyone within a year or two of being taken. Yep. Yes.
How about weather events like solar flares or lightning strikes?
Mm-hmm. The question was about weather events, solar flares, and lightning strikes. Yes, I can confirm that these happen. It's interesting. So lightning is something we deal with all the time. The VLA antennas get hit by lightning all the time, and so they're grounded, and we pay attention to that. Now, anyone who knows about lightning knows that lightning is very special, and you can get hit 5 times, and the 6th time something weird will happen and burst into flame, kind of thing. So we at the VLA right now, we deal with a low level of lightning damage every year. So yeah, that's a thing. I don't have control over that, so that's what it is. Regarding the solar flare thing, yeah, it's interesting. That's actually, we would call that research, is we can detect the impacts of solar events and, these things sort of washing over the Earth. So yeah, we look forward to that. Doesn't so much have, as was mentioned earlier, we're fibering the data back. And so, it's not like radio comms or anything like that. But yeah, lightning is, living here in New Mexico for many years, I developed a very, very healthy respect for lightning, for sure.
Especially that.
Yeah, I know. Yeah. Okay, well, if there are no more questions, take us out.
Well, I just want to thank all of you for coming, and please keep your ears and eyes open as you learn more. You'll start to see more and more about this project. Hope that you do keep in touch. We have information on our website. You can keep up with what's happening with the project. And again, please come back to the VLA if you've been, and if you haven't been, please come out and visit us. So
on Saturday.
On Saturday would be great. Well, on Saturday, our open house will have all kinds of experts there, taking folks on tours. There'll be talks. There'll be things to see. It's a special event, but we're actually open to visitors during the daytime, just on regular days. You can find, if you just Google visit the VLA, you'll find information about how you can come on out. And every Saturday we do tours. This particular Saturday is very special. And if you have to come on a non-Saturday, you can take a self-guided walking tour and see the place. So I encourage you to do that. And I think that's where I'll stop.
Thank you. Okay, so thanks for coming.